Okay, hello everyone. Welcome to the lecture today. And please confirm that you can hear me clearly and you can see my screen. Okay, thank you. So also please let me remind you that I released this instructor evaluation form, or not a form, it's an ungraded quiz. So please spare some time, like it will not take more than 5 minutes uh, to respond to it so that I can get your feedback. And then based on that, maybe I need to make some changes in my teaching style for the rest of the semester. Okay. So having said that, in last week we were basically talking about branch instructions, right? Conditional branch instructions, and we talked about instructions like branch equal, branch same or higher, branch low, branch if carry is set, branch if carry is cleared, right? And all these instructions, they basically look or they basically test the Z flag or the carry flag of the status register for certain values. For example, branch equal checks like if the Z flag is set or not, right? So if it is equal to 1, then the branch is taken, right? And branch if not equal, it tests the Z flag for value of 0. If it is equal to 0, then the branch is taken, right? And then we also had a couple of examples on how we can write the if-else statements in assembly language. So today we will basically start from the same point where we left. So this is the example we actually did last time, but I think I didn't have enough time to go through the solution. So maybe just to refresh your memory, please try to write the code again for the same control flow diagram. For this diagram, write the code in assembly language, and then I will, if needed, I will uh, explain the solution. Okay. So go ahead and do it on your notebooks. I'm sorry. And when you are done, please let me know. Okay. So now let me walk you through the solution. So what we need to do here is, like, we are simply first loading 5 in R17 using load immediate instruction. Then we are you are we are comparing. Uh, Actually, you can use sub instruction, you can do subtract, or you can do comparison. It will have the same impact. Why? Because both sub and compare instruction, they will affect the flags in the status register, right? So, for example, if you use sub R21, R22, so it will like R20 will be subtracted from R21, and then the flag will be set, right? Now, here we are using this version. Like the original one says if R20 is greater than R21, which is equivalent of saying if R21 is less than R20, right? So we are testing if branch if low. So we are saying branch if R21 is low than R20, right? And if so, then we are saying go to the label which says if. And in that part, we are saying increment R22, this part here, right? And then after that, increment R17, right? But in the case where this condition is not true, where R21 is not lower than R20, which means it is equal to R20 or greater than R20, then this jump will be not taken, right? And the control will go to the next instruction, right? And by the way, I don't think if I explained it in the previous lecture or not, but if you put a comma before any instruction in the assembly language, and at least in assembly of like assembler of ATmega328P, then it is treated as comment. So this instruction is basically commented, right? So I will explain I commented it, but for now, let's assume that the condition is this condition is false. So the control don't go to the if statement or if label. So the next instruction that will be executed is decrement R22, which is this one, right? Here. And then we are saying R jump next, or you can only simply say jump next. If like, because we have not yet covered how what is like R jump, it is relative jump actually, but we haven't talked about what is the jump instruction, how it works, or what is the relative jump and what is the difference between them. But for now, you can just it is sufficient for you to know that it is basically saying go to the this label without testing any condition. So this is like unconditional jump. You are going to this label without testing any condition. But these branch instructions, these are conditional jumps. Okay. So you are saying go to the next. So the next will be this one, increment R17 here, right? Now, let me go back to the question why I have commented this instruction. Actually, you can use one of these two instructions, which I'm now putting in a rectangle. So you can use one of these instructions. Both are doing the same thing. So branch low is saying like if R21 is less than R20, right? And in the second instruction, which is commented, is saying branch if carry is set. Now, if you remember from the previous lecture, whenever you are doing A minus B and where A is less than B, then what you will see is that as a result of this subtract operation, what will happen that carry will be set, right? So what we are saying here is necessarily the same thing. We are saying branch if carry is set, which is another way of saying branch if low. Okay. Any questions? Okay. If no questions, then let me erase these annotations so that, okay. So you can write the program in another way also, like where what you are doing is basically you rewrite this condition. How you can rewrite this condition? The condition is if R21 is less than R20, or you can say like if R20 is you can actually reverse it. So you can say if R21 is greater than or equal to, right? So if you reverse the condition, so this part will be like this path will be taken when when this green condition is true, and this path will be taken when the green condition, this one is false, right? So we are just switching. Remember, if you remember from the like I am just flipping the condition. So if I'm flipping the condition, the paths that will be taken will also be flipped. The yes path will become no, and no path will become yes path, right? So now if you do that, so here what we are doing exactly the same thing. We are first putting 5 in R17, then we are comparing R21 with R20, and now we are saying if R21 is same or higher, branch if same or higher, then go to the else part, right? So the else part is what? Decrement R22, right? And then go to increment R17. But if it is not greater than or equal to 20, if the condition is false, then don't go to the else part. Do the next instruction, which is increment R22, and then go to the R jump text, which is R17, increment R17 here. And again, if you see here, we have commented and this next instruction, branch if carry is cleared. So which is basically doing the same thing again. If we are doing A minus B, right, such that uh, A is uh, equal to or greater than B, then what will happen is that your carry will be cleared, right? So that's why we are saying branch if carry is cleared. So it is same thing as saying branch if same or higher. So if you are not super clear on this, I would advise you to go back and go through the lecture of the previous recorded lecture, right? Last lecture. So because there we have discussed how carry and Z flag are set when A is when you do A minus B, and where A is equal to B or A is greater than B or A is less than B. Okay. Any questions? No? Okay. So at this until this point we have learned how to write an if statement and an if else statement in assembly language. Now we are going to talk about how we can do loops, like for example do while loop or for loop, right? So what is like how the do while loop works? So it's typically when you write a do while loop, you initially do some initialization, right? You set variable to certain value, then you enter the loop, and in the first iteration you do not test any condition, right? And then you do something in the body of the loop, and you also calculate the condition or update the condition variable which you are going to test, and you then test the condition. Now if the condition is true, you go back in the body of the loop, otherwise you exit, right? So this is how on the right side this shows how the control flow uh, works in case of the do while loop. You have an initialization block, then you do something in the body of the block. You calculate or update the condition variable, then you test the condition, and if it is true, you go back in the body. Otherwise, you exit the body of the loop. So now let's try to learn writing do while loop in assembly language through an example. So what we want to do is to write a program which executes the instruction add R30 and R30 and R31 nine times, right? So we are like simply running the loop nine times. So here is like the control flow diagram of the program which we want to write. So you are what we are going to do is we will put R9 in R16. Why? Because we will use R16 as our variable. We will every time what we will do is that we will decrement the value of R16, and if it is not zero, we will keep adding R30 and R31. So here we are initializing R16 with 9, then we are adding the R30 and R31 together, then we are decrementing R16, which is basically our condition variable. It serves as a condition variable. And then we are testing if R16 is greater than 0, then go back and add R30 and R31 once more. If not, if it has become equal to 0 R16, then we stop or terminate our loop, right? Is everyone clear on what we are going to do, right? Like what we are going to code? Okay. So now let's have a look. So you know what is this directive.org. So we are basically saying that whatever we are going to write, put it in the code memory, right? Now here we are first loading 9 in R16 through load immediate instruction. Then we are saying add the two registers R30 and R31, then decrement R16, right? And then we are using the instruction branch not equal. Why? Because we are saying if R16 is greater than 0. So basically we are saying that if R16, so we are basically, we can say, remember I said that it's always better to flip the condition. So if R16 is equal to, so if it is not equal to 0, so since we initially have R16 equal to 9 and every time we are decrementing, so as long as it is not equal to 0, we need to go back to the loop, right? So this is what we are saying. We are saying branch not equal L1. So this instruction, it will do what? It will look at the Z flag, the value of the Z flag, which last instruction will affect the value of Z flag decrement, because in decrement you are doing basically subtraction, right? R16 minus 1. So Z flag will be affected. So if the value of R16 is if the value of R16 is not equal to 0, your Z flag will be equal to 0, right? But when you will keep decrementing and finally it will become 0, become equal to 0, then Z flag will be set equal to 1, right? So when you say branch not equal, so your hardware or this instruction, what it does, that uh, it will branch to the label L1 when your Z flag is equal to 0. So if Z flag is equal to 0, this instruction will go back to the loop 1, because when uh, ask when will R16 become equal to 0, when we, how we know it, by looking at the Z flag. When Z flag is equal to 1, so it's mean that we are done, right? And then at that time point this condition will become false and the control will fall to the next instruction or continue to the next instruction, which we are doing nothing, but we are just saying keep jumping at the same instruction, like R jump L2, which basically is saying we are saying go to label L2. So L2 is actually the label of the same instruction. So it will be an infinite loop here at this point, right? Any questions? Okay, so if no questions, okay, yeah, there is one more point which let me discuss this. Uh, so what does it mean? K is equal to minus 3 in branch not equal L1. So this instruction basically, right? So here, remember what was K? K is like where how the value of the PC will be updated, right? So initially PC is pointing at branch and branch not equal, this current instruction. Let me just change the color so that it becomes clear. So PC is pointing at branch not equal, right? What is PC plus 1? PC plus 1 is the next instruction, right? Now, if you remember how the value of the PC is affected if this instruction is executed and the branch is taken, the new value of PC becomes PC plus 1 plus K, right? Now, what should be the, so here what we are asking is this, that what should be the value of K such that if the branch is taken, the control goes back to L1. So remember, this is PC plus 1 here, right? So we need to add the we need to set the value of K such that we point to this instruction, right? So which means minus 1, minus 2, we are going back, right? Minus 3, because our branch is backward, in the backward direction. So that's why K is equal to minus 3 in branch not equal L1 instruction. And in case of R jump L2, we have not yet discussed this relative jump instruction, but uh, it also updates the program counter, right? And here again, it actually uses the same mechanism. So if you're executing the R jump instruction, PC will be pointing here, right? So this will be PC1, PC, and the next instruction, whatever instruction you have here, let me indicate it by X. So for this, the PC will be PC plus 1, right? But if this R jump instruction is executed, how the value of the PC will be set using the same mechanism, this one, right? So what value we should set k, what should be the value of k such that the updated value of PC becomes same as L2, right? So it should be equal to -1, right? Because we are going back. So here -1, -1, 1 from relative to this point, PC plus 1. Any questions? Okay, I think it will be better if we do the next slide as an exercise. So here you are supposed to write a program which calculates the result of summing the numbers 9 down to 1. Okay, and on the right side you have the control flow diagram. So let me not explain the control flow diagram to you. Have a look at it, try to understand it, and then write the code. If you need, and I will actually recommend you to like flip this condition uh, and then write the assembly program. Okay. And also, when you write the assembly program, after that, tell me what will be the value of k which will be used in the branch instruction. Okay. Go ahead. So let me know when you are done. Thank you. Let's wait for other people to complete. I need at least two more people to say done so that I can go ahead. Okay. Thank you. Okay. So I think all think this part is straightforward, right? So you are simply putting 9 in R16 and then 0 in R17. Then you are saying add R16, R17. Why we are putting 9 in R16? Because we are going to, what we will do, we will keep checking if is it equal to 0. If not, we will add it to R17. So initially we put 0 in R17 and then we'll keep reducing the R19, R16. So we are adding R16 and R17 together, right? And then we are saying decrement R16, which is serving as our conditional variable, like condition variable. And then we are saying branch if not equal. So which, remember, when we do decrement, initially it is 9. So then it will become 8, then it will become 7, then it will become 6, and so on. So up to 1, this condition will be false. Why? Because the value of R16 register will not be equal to 0, so z will be equal to 0, right? So we are saying branch if not equal. So in that case, your loop will go back to L1. But once the value falls down or reduces from 1 to 0, so your value in R16 will become 0 and Z flag will be equal to 1. So this condition will not be true anymore, and the control goes to the next instruction, right? Okay. So what will be the value of K here? What will the value? Remember how the value of program counter is set when you take the branch PC is equal to PC plus 1 plus K. So what will be the case such that the branch is taken back to the label 1, L1? Yeah, minus 3, right? Because this is PC plus 1, this is PC plus 1, and we need to add K to PC plus 1, right? So minus 1, minus 2, and minus 3. Thank you. Okay, let's continue. Now, in this example, you need to write a program which calculates the result of number 20 plus 19. So 20 down to 1. Okay. And again, you have the control flow diagram on the right. Have a look at it and then write the program in assembly language. Let me know when you are done. Okay, thank you. Let's wait for some more people to complete. Thank you. Okay, let me show you the solution, right? Thank you, Logan. Okay, so it is pretty similar as what we did in the last slide, right? The only difference is that this time we are adding 20 down to 1 instead of 10 down to 1. So you are putting 20 in R16, you are initializing R17 to 0, then you will keep adding R17 and R16, and in every iteration you are decrementing R16 by 1, and then you are testing if it has become equal to 0. If not, so then go back, and if it has become equal to 0, then go to the next instruction, which is an infinite loop, right? And again, the value here of k will be equal to -3, right? K for branch not equal, but for our jump, it will be -1, right? Okay, another example. Write a program. Okay, I know that the program is shown. Let me just simply quickly animate it. Okay. So write a program which calculates the numbers from sum of the numbers from 1 to 27, odd numbers from 1 to 27. So 1 plus 3 plus 5. So you need to skip 2, and then you need to skip 4, and then you need to skip 7. So add all of them from 1 to 27. Okay. So again, you have the control flow diagram on the right side. So try to encode it in assembly. Let me know when you are done. I know you might be struggling with encoding this condition R16 is less than equal to 27. If you are struggling, then remember you can always modify the condition without affecting the correctness of the program, right? Okay, I think it's better if I show the solution, right? I just wanted you to give it a try. If you are not able to do it, it's fine. Okay. So here this part is straightforward again, the part before the condition, right? So we are simply putting 0 in R20, and then we are loading 1 in R16, right? Then we are adding R16 and R21. So it is basically 0 plus 1. And then we are incrementing R16 by 2, right? So we adding, so actually, uh, this instruction is not correct. I think it should be add immediate. There is an instruction which says add I, okay, which have we have not covered. But if you don't know add immediate exists, what you can do is this. You can put, for example, 2 in another register initially here, maybe at this point. You can put load immediate and R17 2 And here you can, instead of 2, you can put R17, right? So now you have incremented R16, sorry, this is 17. So you have incremented R16 by 2 now, right? So now it was initially 1, now it has become 3, right? And now you are comparing R16 with 29. That is what I meant, is like you can modify this instruction. So we can say this condition. So we can say, if instead of saying R16 is less than equal to 27, so we can say R16 is the not equal to 29. So if it is not equal to 29, so then go back. But if it is equal to 29, then end the program or terminate the loop, right? So here is what we are doing. So we are saying compare R16 with 29, right? And again, we have not covered compare. Actually, compare instruction also has two versions, compare and compare immediate. So in compare, you must compare two registers, but in compare immediate, the second operand can be an immediate number, right? So here we are saying now compare R16 with 29. So if, and then we are saying if it is not equal, right? So then go back. If it is not equal to R16 is not equal to 29, then go back to L1. Remember, what does the compare instruction do? It will subtract 29 from content of R16, right? So when the content of R16 is equal to 29, what will happen? That the result will be 0. So if the result will be 0, then Z will be equal to 1, and this branch will not be taken. But before that mean when value of R16 is less than 29, then the value of Z will be equal to 0, and the branch will be taken. Taken mean it will go back. Okay. Uh, and what will be the value of K here? So in this particular case, remember PC plus 1 points to the next instruction, right? So it will be -1, -2, -3, -4. So the value of the K will be equal to -4, and that then like the PC will be set equal to the address of this instruction. Okay. Any question? Confusion? No? Okay. Okay, so until this point, we have talked about the branch conditions, which basically perform the branching based on the result of comparing two unsigned numbers, right? So when we compare two unsigned numbers, what happens? Z and carry flag, their values are affected, and then we use the branch instructions, which test either the value of Z or the value of C flag uh, for a particular fixed value like 1 or 0, right? So but what if the numbers which we are comparing, like for example, the registers which hold the numbers, what if I consider those numbers not as, interpret those numbers not as unsigned number but as signed numbers? So then, can I still use the same instructions like branch if low, branch if same or higher, branch if carries set, branch if carries cleared, right? So can I still use the same instructions or not? So it turns out that we cannot use the same instructions. Why? Again, because those instructions test Z flag or carry flag, right? But the value of carry flag uh, is not, it doesn't convey you the right information or the correct information when you are comparing the signed numbers. So you cannot rely on the carry flag when you are comparing the signed numbers, and as a result, we cannot use branch if same or higher, or branch if low, or branch if carry is set, or branch if carry is cleared, right? Because they test the value of the C flag. So as long as you are comparing the unsigned numbers, fine, you can use them. Branch same, branch like branch if same or higher, branch lower, low, branch carry is set, branch carry is cleared. But when you are comparing signed numbers, you cannot use them. And I will show you like why we cannot, why the carry flag doesn't give you the correct information when you are comparing the signed numbers. Okay. But I will show you in the later slides, but for now, you can trust me, okay? In a couple of slides, I will explain it, okay? So when you comparing the signed numbers, so C flag is not enough. So we need to involve three other flags, or we need to understand three other flags. So which are negative flag, overflow flag, and sign flag. So these flags are meaningful only for signed numbers. So let's say that X is the true result of an instruction. So what does it mean? So true result of an instruction mean that the result of comparison. Okay, so result of comparing two numbers, right? Sorry, not result. The n is the true result of an instruction. For example, add instruction. You add two signed numbers, you subtract two signed numbers, right? So n, it is the actual. If n tells us that the actual result is negative, so this bit or this flag in status register will be set equal to one. If it is set equal to one, it's mean that the result is negative. But again, this flag is meaningful only when we know that the numbers we are working with, they are signed numbers. If the numbers you are working with are unsigned numbers, then you don't need to care about n flag or s flag. Okay. And if this bit is equal to zero, then it's mean that result of our result of adding two signed numbers or two subtracting two signed numbers is positive. So n flag is incorrect when overflow occurs. So this like this is like the significance or how you interpret the n flag. However, if there is an overflow, then you cannot trust the n flag. Then in that case, the information conveyed by n flag will be false if there is an overflow. What do I mean by overflow? I will explain. Okay. So uh, all of our registers they are 8-bit registers, right? So for example, if you add two registers, so the result of the addition will be stored in an 8-bit register, right? Now if we are the result which is stored in a 8-bit register, if we are treating it as a signed number, right? So what is the range of 8-bit signed number? It is from minus 128, including 128, to 127, right? So if the result which is stored in that bit, which the result of that instruction, for example, you are adding two number and the results become greater than 127. So it cannot be stored in an 8-bit register. Similarly, let's say if you did the subtraction and the result is smaller than minus 128, you can still not hold it in a 8-bit numbers, no 8-bit register, right? So it's mean that there is overflow. The result you are getting is out of the range and there is overflow. And in that case, your V flag will be set equal to 1. But if there is no overflow, so V flag will be set equal to 0, which means that if your result is within this range, right? So if your result is greater than equal to minus 128 and less than 127, right? Again, if your V flag is equal to 0, which means there is a no flag, then the information conveyed by N flag, a negative flag, is correct. You can trust it. However, if there is overflow, then you cannot trust the value or information conveyed by the negative flag. So if for example, if there is overflow and you look at the negative flag and it says n is equal to 1, so if you cannot uh, trust that yes, the result is negative, right? However, if v is equal to 0, there is no overflow, n is equal to 1, then we are sure that our result is negative. Similarly, if v is equal to 0 and n is equal to 0, we are sure that our result is positive. Okay. But if v is equal to 1 and n is equal to 1, we cannot say anything. Maybe our result is positive and false information is shown by n is equal to 1, or maybe our result is negative. Okay. So we cannot trust. So if since we cannot trust the n flag when we have an overflow, that's why we have an additional flag s, which stands for the sign flag, and it is basically the exclusive OR operation between N flag and V flag, right? And this S flag always gives you the correct information. Remember, N gives you the correct information only when there is no overflow, but there is overflow and you cannot trust N. However, the sign flag, it also always tells you the correct information. If sun flag is equal to 1, it's mean the result of operation which you performed on two signed numbers is negative. If s is equal to 0, it's mean that the result of operation which you did on the two signed numbers is positive. Okay. So s is equal to true when x, which is basically the result, is less than 0, and s is equal to 0 when x is greater, the result of operation is greater than or equal to 0. Okay. If you have any questions at any point, stop me. Okay. So we covered these flags, zero, C flag and Z flag earlier, right? We also talked about what is this half carry flag. Uh, Now let's talk about these three flags N, V, and S. Okay, N flag, so it is negative flag and always equal. Its value is always same is equals to the bit 7 in the result. So, and you can trust it when there is no overflow, as I said earlier, but the value information conveyed by N is incorrect when there is overflow, right? So here is an example. Suppose you add two numbers 96 and 70, right? And we are considering them as signed numbers, right? Remember, the N, V, and S flag, they are meaningful only when we are treating our numbers as signed numbers. If we know that the numbers we are processing, they are unsigned numbers, so we don't need to care about these flags. Okay. So, okay, so now we are adding these numbers, and these are 8-bit numbers. Both of them are positive, right? So when you do the addition, so you will see that you get this answer, right? So the answer is 166, right? So remember, our result is 8-bit, right? Our result is 8-bit, but and we are treating the signed bit number, all the numbers as signed numbers, right? So what is the range? The range of the 8-bit signed number is 128 to 127, right? So it's mean that our result is out of range, 166. It is greater than 127, right? So now this most significant bit of the result is basically set as the value of the n flag. So n is equal to 1, right? So what it is, what if I look at n, what information I get? That my result is negative, which is wrong, right? My result is positive, but the problem is that it is greater than 127, so it cannot be contained in 8-bit register. So there is an overflow. So since there was an overflow, that's why n is giving me wrong information here. The result is supposed to be positive, 166, right? The true result is greater than 127, which is out of range for 8-bit signed positive number, and therefore the overflow occurs. Okay, so the actual result is negative with n is equal to. So here the true result is like 166, but the actual result which we see in the register, if we look at this 8-bit number, so it is a negative number. Why it is a negative number? Can anyone convert? Can you convert this 10100110, treat it as a signed number and convert it into the decimal form? Treat it as an 8-bit signed number and convert it into the decimal form. Go ahead, you have 30 seconds. So if you're done, let me know. Okay, let's wait some more people for some more people. Yeah. Okay. So the result will be like you can simply like let me write the weights, right? So for those digit bits which have zero, I'm not writing the weights, right? So 0, 1 plus 2 plus 4, 1, 2, 4, 8, 16, 32. And remember, it is a signed number. So the weight of most significant bit is what? Negative, right? So it will be minus 128. So minus 128 plus 32 plus 4 plus 2, when you do the math, you get minus 90, right? So the result, the actual result, the actual mean, the result which is in your register, stored in your register, it says the register says that result is equal to minus 90, right? Which is wrong. When you add two numbers, two positive numbers, the result is always positive. So it's mean that we cannot trust the N flag, right? Because N flag is what? N flag is 1, which is wrong because there is overflow. Any question on previous slide? Okay, so uh, let's see how the value of our flow flag is set. So V flag, it indicates that our flow of indicates our flow of signed arithmetic operation. So V is set to 1 if and only if either of the conditions below occurs. Like if any one of the following two condition is true, the value of V will be set equal to 1. If there is a carry from D6 to D7 in the result, when you do the operation, there is a carry from D6 to D7, but no carry out of D7. Or there is a carry from D7 out, but no carry from D6 to D7. Okay. So here is example. So you have two numbers 96 and 70, and you are treating them as signed numbers again. So when you do the math, so you will see that actually if I add only the numbers at this position, so let's say I start adding from this one. So 1 plus 0 will be 1. So there is no carry into from like uh, so that is D5, okay. And then 1 plus 1 is 0, 1. So there is a carry from D6 into D7, right? So there is a carry. And then 1 plus 0 is 1. So there is no carry out, right? So carry from D6 to D7, but no carry out of D7, right? So which condition is true? This one, first condition is true, right? So our flow flag will be set equal to 1. So since our flow flag is set equal to 1, and n is equal to n is this one, right? So n is equal to 1, but we cannot trust n. Why? Because we know that overflow has occurred, right? So we cannot trust n. And what will be the value of s? We will see in the next slide, but s is exclusive r of n flag and v flag. So if both are 1, and if you remember how exclusive r work, s is equal to 0, right? And if s is equal to 0, it basically tells us that the result is positive, right? And this is correct because when you add two number 96 and 17, the result should be positive, right? So S is giving us the correct information. N is giving us wrong information. Why? Because we know that overflow occurred. And if overflow occurs, we cannot trust N flag. We must look at S flag. S flag, always you need to look at S flag because it will always give you the correct information. N will give you correct information only when there is no overflow. Any questions? Okay, here is another example. Okay. So we are adding two numbers minus 128 and minus 2, right? So there will be no carry from D6 to D7, right? But there will be carry out from D7, right? So it's mean that our flow occurred, right? So V is equal to 1. So this condition is true, right? And what is value of N flag here? Can anybody tell me what will be the value of N flag? Yeah, 0. So this one, right? So n is equal to 0. And what will the value of S flag? Can anybody tell me? value of S flag. Yeah. So it will be equal to 1, right? So again, since we have an overflow, N will not give us the correct information. So this is wrong, right? So we always look at S. N will give us wrong information. Now if we look at S is equal to 1, which means what? That the true result is negative, right? And it should be negative because you are adding two negative numbers. So it is minus 130. So S gives us correct information while N is telling us that result is positive, which is wrong. Okay. Now the third flag is sign flag. Actually, I already have explained how it works, but let me go through this slide. I'll read this slide. So sign flag, S is exclusive OR between N and V flags. So S is N exclusive OR V. And uh, so here is another example. You are adding two numbers, minus 2 and minus 5. So result should be minus 7. So when you will do the operation, you will find that there is no overflow. Why there is no overflow? Because there will be carry out from D6 to D7 and there will be also a carry out from D7. Remember, we said that overflow flag is set only if one of those condition is true. But in this case, we have both conditions are true. That's why V is equal to 0, right? And in this case, now N is equal to what? 1. So it is giving us correct information. We can trust it in this case. But if we look at S is also giving us correct information because S is what? Exclusive OR of N and V. So one exclusive OR 0 is 1, right? So it's always better. You can simply always look at S is equal to 1 instead of like uh, confusing when to look at N and when to not look at N. Here is another example. So there is no carry out from D6 to D7 and there is no carry out from out of D7. So both conditions are false. So V is equal to 0. So N is equal to 0 and S is equal to 0. So S always gives you the correct information. So it is telling us that the result is positive and it should be because we are adding 7 and 18 which are both positive and they result in 25. Okay. Remember, all this discussion is in context of signed numbers. Here is another example. So there is no carry out from D6 to D7, but there is carry out from D7, right? So it's mean that we have a overflow. So V is equal to 1. And now when we look at result, N flag tells us that result is positive, which is wrong because we are adding two negative numbers, minus 120 and 1 minus 2. So it will be minus 130. So, but if we look at S, which is exclusive OR of N flag and V flag, so its value is 1, which tells us that result is negative, which is the true case. Okay. So now if A, let's say like you have two numbers A and B, and let's say if we consider them as unsigned numbers, like then we can use branch low and branch same or higher instructions, right? As I explained earlier. Why? Because they rely on the C flag, right? So we can rely on the C flag when the numbers which we are comparing, they are unsigned numbers, and since branch low or branch same or higher or branch if carry is set or branch if carry is clear, all of them test the C flag and C flag is correctly set or it correctly compares the unsigned numbers. So we are fine with those instructions, right? However, if A and B are considered signed numbers, then branch low and branch same and higher as higher will not always work correctly after A minus B subtraction, right, because carry will not give you the correct information on the relationship of the two numbers, whether A is greater than B or A is less than B. So you can rely on C flag only if the numbers are unsigned, right? So what should we do if we cannot rely on C for signed numbers, carry flag? So for that we use the instruction branch less than and branch greater than or equal for signed number comparison, right? So branch less than, it will branch if A is less than B, and branch greater, it will go to the destination loop or destination target address if A is greater than or equal to B, right? And these two, both of these instructions, they actually test the S flag of the status register, right? So branch less than, it will test that it will take the jump if s is equal to 1, and branch greater than or equal to, it will jump if s is equal to 0, right? Which means that number is positive. A is positive, right? A is greater than or equal to B. Result is positive. Sorry for saying number. So this is just truth table of how S flag is computed as exclusive OR of N and V. So it is 1 when only one of the input is 1. Like either N is 1 or overflow flag is 1. If both are 0 or both are 1, then result is 0. Result is 0. Okay. Uh, what is the purpose of this table? The purpose of this table is following. It is actually emphasizing this point. Like if numbers are unsigned, we cannot rely on the C flag because sometimes C will give us correct information and sometimes it will give us incorrect information, right? So we can not rely on the C. So it is just highlighting that. Okay. So here you have in column A and B, here you have different values of A and B, 10, 10 and 8. So, and what you are doing, A minus B truth, right? Truth mean that what the value should be, and A minus B actual mean the value which is contained in your register, 8-bit register, right? So if you have A is equal to 10, B is equal to 2, and you perform A minus B, so carry flag will be equal to 0, right? So which is telling what? Which is, if you remember, it is telling us that A is greater than or equal to B. So we can trust. In this case, we can trust, right? So in this particular example, right? So A, so these green cases, in these green examples, we can trust C is giving us the correct information, right? But in these particular values of A and B, and I am doing A minus B operation, right? So the value of C is equal to 1 and 0. For example, here A is equal to 2, right? And B is equal to minus 1, and I am doing A minus B. So when I do A minus B, what will be the result? It will be 2 minus minus 1, so it will basically 3, right? So the result is what? Result is positive. So here when I compare, 2 is greater than B, right? But the carry flag is set. When carry flag is set, if you remember from the previous lecture, if the carry flag is set, it's mean that A is smaller than B, which is not true. True, 2 is greater than B, right? So we cannot trust the carry flag. So the point here is that sometime carry flag will give you correct information, sometime carry flag will be giving you incorrect information when you are treating numbers as signed numbers, right? So that's why it's always better to only look at your sign flag to get the information about whether the result is whether the two numbers are positive or not, like A is greater than B, or A is same as B, or A is less than B, right? So here only S flag is consistent to determine if A is greater than or equal to B. C is not consistent. Sometime it is correct, sometime it is incorrect, right? N is also not consistent. It is sometime correct and sometime incorrect. For example, in the last case, right? Okay. So in next couple of slides, I am just trying to emphasize or like embed this understanding in your mind what we have discussed in the previous slide, like when we are treating numbers as signed numbers, unsigned numbers, we can rely on the carry flag. But if we are treating numbers as signed numbers, we cannot rely on the carry flag. Actually, on any other flag, we must rely on the S flag, right? So here is an example. And here, when I say in this example, we are using unsigned numbers. Okay. So A is equal to 10. So what is that 4-bit binary of 10? 1010, right? B is equal to 8. What is 4-bit binary of 8? 1000. Remember, I am treating the numbers as unsigned numbers, which mean most significant weight of most significant bit is positive, right? So when I do the subtraction a minus b, so I simply do the binary subtraction. I don't want to go through the like steps, but when you will do it, you will find the result is 0, 0, 1, 0, right? Which is equal to 2. So when you do 10 minus 10 minus 8, the result is 2, which is correct, right? So C is equal to 0. So it is telling me when C is equal to 0, what does it tell me? It tells me like there was no carry out here, right? So it is telling me that A is greater than or equal to B, right? So 10 is greater than or equal to B, equal to 8, right? So I can trust C because I am treating my numbers as unsigned numbers. Here is another example. I'm treating A is equal to, I'm again treating numbers as unsigned numbers. So A is equal to 8, B is equal to 10. So 4-bit binary of A is 1000, 4-bit binary of B is 101, 1010, and I'm doing A minus B, right? So when I do A minus B, here I have shown you the steps, right? So the result will be 1110, right? So there is a carry in most significant bit positions. So C is equal to 1, right? So when C is equal to 1, what does it tell me? It tells me that A is less than B, which is true because A is equal to 8 and B is equal to 10. So again, this is another proof that when I'm treating unsigned, another example, when I'm treating numbers as unsigned numbers, I can trust on C. So these are all the example where we are treating numbers as unsigned numbers and carry flag give us the correct information, right? Again, here I don't want to go through like the binary version, but A is equal to -2, B is equal to -1, right? So wait a minute. So here we are not treating them as in this example we are not treating the numbers as uh, yeah, so I am actually getting the what is this called? Two's complement form, right? So -2. So I'm calculating -2 by first taking the ones complement, then adding 1 to it, and I get the binary form of -2, right? And B is equal to -1, so it is all ones. Now when I do A minus B, right? So I will get this result, and here, since there is carry in the most significant bit position, C is equal to 1. So when C is equal to 1, uh, it tells me like, hmm, okay, let me stop here. I think I am not clear on this example. I need to think about it again, and I will start it again in the next lecture at the same point. Okay. So let me stop here. I don't want you to misguide you. So let me stop here, and we can have a look at this example in the next lecture. Any questions? But again, the information which I shared with you is correct. Like we can trust the carry flag only when the numbers are unsigned numbers. But if the numbers we are using in our operation, arithmetic operation, they are signed numbers, we cannot trust the carry flag to get the information whether A is greater than B or A is equal to B or A is less than B. Okay. So again, I will have a look at this example and explain it to you in next lecture. So do you have any questions at this point? No? Okay, if no questions, then that's all for now. And see you in next lecture on Wednesday. You too. Have a nice day. Thank you.